Duplicate just a moment, then duplicate I have to change back moment. So it cannot take extended here, right? Whereas in the morning it was alright. I mean, I don't need it right now, speaker knows much, but okay, now so you guys always change the settings and okay, moment, let me see if it works on the possibly, yeah, now it's worked. Okay, so everything alright, set. So yeah, here we stopped. So I mean, talking about the phase synchrony. So I will introduce some other related measures, primarily with the aim of estimating functional connectivity. The next one, kind of, which is based on the concept of generalized synchronization. So it is based in nonlinear dynamical system theory. There. So if you recall that we were treating functional connectivity as kind of statistical interdependence. We didn't specify what kind of interdependence, some aspect of interaction. So generalized synchronization actually assumes or that there is some kind of mathematical function which maps one signal to another signal. So you have a signal X, signal Y. These two signals are somehow related by a map which is mathematically smooth between the dynamics of two processors. So it is. Suppose again, as I said here, sorry, it doesn't. So this is your signal X, and as one is signal Y, preferably coming from two different systems. Now you are assuming these two signals somehow related by some mathematical map, which is smooth. So now how we can find out not the exact nature of the map, but whether they are at all related by some mapping or not. And this problem is addressed or can be formulated in the framework of nonlinear dynamical system theory we talked about yesterday. So what you first do, you first from each time series you do phase space reconstruction. So you consider state space vectors and then choose embedding dimension and tau separately for each time series, and then you reconstruct your state space in each state space. And then suppose this is again here I am giving a kind of schematic. So this is your time series, and this is suppose your reference vector at this point in time t. And then now looking at which other vectors in the same state space are its neighbors, means geometrically close. There. So this is the inside the state space. So but here I am showing you here in the time series here. So these two part of the time series, means these two state vectors, they are actually geometrically very close to it. Remember, here I am talking about geometrical distance, not just temporal distance. There. So means these two time series, I mean state vector is also kind of small time series, you can say so. They are looking very similar to your reference vector. So here, so this is if you go into the state space, so you have state vector xt there, and then you're searching in your state space, finding what are the other state vectors which are close in Euclidean sense, and you remember their time points there. And then the idea is, if the two systems X and Y, they both evolve in their individual state space, if the two systems somehow sharing information, there is a mutual exchange between the two systems, then the neighborhood in one state space would also mapped into the neighborhood of other state space there. So that's what we call the kind of neighborhood mapping or topological relationship there. So what does it mean? Sorry, here again. So if you have, so this is your suppose state reference vector, and you create a reference, you create a kind of neighborhood of different state space vectors, and then you try to find there. Okay, and also you have an same reference vectors or the same time indices in the y state space, and you also find its nearest neighbors in the other state space there. If there is a map between relating system x with system y, then the time indices of these neighbors would be very similar. How we can do that? We just project from one state space to another state space. So here, so that's the red one is its original neighbor, means these red vectors are literally close to my reference vectors rk. And now I know, suppose I found x67, that means 67th instant, or x81 or x122, these three vectors are very close to the reference vector xrk. Fine. Now I go to the state space y. Now I find the same reference vector with the same time indices yrk. Let us see the state vector y at the same point at the other state space. And then now I remember earlier whatever I say 67, 81, 129, those are the time reference vectors were close to the states in the state space x. Now I see, let us see where are the state vectors in y at that time point. So y81, y67, y129 there. And if the two systems share information, if there is a map, then these three we call it mutual neighbors there would also lie very close to the yrk there. So that's the idea. Okay, again it's gone. Okay, so here, so these are the red one is the original neighbors in its own state space. You remember the time points, and then you see in the y state, what are the y state vectors doing with the same time points of the x neighbors? Do they also form a cluster or do they spread there? If they remain as a cluster around your reference vector in y, then that's a good evidence that two systems share information. And you can also do it in the other way around. You also have the reference vectors clustering or the neighbors clustering around in the y state space. You remember their time indices, and then you check the same time points what happens to the x state space x there. So this way you can kind of distinguish the influence of one system from the other direction. So this is an asymmetric index, and what I mean the index you can prepare here is primarily compares the neighborhood size there. Neighborhood consists of true neighbors, means which are the neighbors or state space which are from its own state space, and we call mutual neighbors, the neighbors formed by the time indices coming from another state space there. So that's an idea. So and then you calculate, I mean simple, you apply Euclidean geometry, you can calculate how much clustering is formed in the true as compared to the mutual neighbors. But the idea is, if the two systems are somehow synchronized, then the true neighbor and the mutual neighbor will strongly overlap. If system x influences system y, then you have one directions you have a strong clustering, another direction not there. If both mutually influencing each other, then there will be strong overlap in both state space x and y in terms of true and the mutual neighbors. Okay, just thinking about, I'm just kind of a simple analogy. Suppose if I am telling you, I'm trying to find whether me and you, someone there, sharing information or not. Suppose I can find that, okay, whatever I am doing right now, it is very much influenced by what I was doing yesterday 10 o'clock. And if I am sharing, really have a sharing information each other, then whatever you are doing right now also would be influenced by what you were doing 10 o'clock last night. So that's the idea there. So, you are just using time indices, but switching one state space to another state space there. Okay, so and if you kind of schematically, if this, suppose this is a chaotic system, roster attractor, and then this is a Lorentz attractor, if there is no coupling, then the state space which are close here would be completely spread out in the other state space. If there is a coupling, if the neighbors which are close here would also remain neighbors in the other state space. That's the idea. And then you can come up with a, I mean, you can quantify this proximity, how closely they packed in the different indices. There are different versions of this, but the concept is the same. So that's we call the generalized synchrony there. So here it is actually sensitive to both linear and nonlinear coupling, because you're assuming some kind of map. You don't specify, and also this measure is very appropriate for nonlinear system, and it reveals dynamical interdependency, and they're also very sensitive to weak interdependency. And it doesn't matter whether you're doing it on this frequency band or raw data, it doesn't have any assumption. So means like phase synchrony, which is important the signal to be of narrow band, this restriction doesn't apply here. Some issues, because as you remember from nonlinear time series analysis, you need more data points. For short data is a bit difficult. And it's a computationally also expensive, because always in a state space reconstruction you have to go into search for all the neighbors. They are always computationally more intensive there. And some other mathematical issues, I mean, if you are interested, if the two systems are widely vary in terms of dimensions, that can be problematic, or if the attractors are heterogeneous attractors, then it's a problematic. But there has been quite a bit of research that this kind of approach works pretty well for EEG, MEG signals there, especially if the data are spontaneous. Means when you have a longer segments. So just give a simple example here. So these are 3 pairs of signal, 3 different cases there. It's coming from 2 different hemispheres. Now you have a case A, case B, and case C. Which case or which pair you think has the strongest synchrony, or what is the order? I mean, does you think there case A, case B, and case C, strongest relationship between the 2 within each pair? Which one you think has the strongest? Usually I is a very good, let me tell you. B is the strongest, okay, there, and then A, and then C, okay. Then very likely I think that would be the case, because this is quite okay. So this is, if you apply this linear correlation on this data, yes, you get a B high value, A is just very closely, and then it comes to C. If you apply mutual information there on this data, there B comes out, yes, A and C somehow pretty close there, you cannot discriminate much. If you apply coherence, which is slightly difficult to compare, because coherence is frequency specific depending on which frequency band you're going to choose, and I choose it here a certain low alpha frequency band, because that's where primarily the oscillations lie. So here if you apply coherence, A and B cannot be discriminated much there, C is with a weaker. The Granger causality, if you do it, and here, so here yes, B comes out, okay, the stronger is the Granger causality as well as partial dated coherence in that same frequency band, but A and C is kind of mixed up there. Phase synchrony there within the same frequency band, there A is the strongest, then quite a bit of difference from B to A, and then much stronger separations from A to C. And if you do a nonlinear index, this generalized synchrony, it's kind of reasonably separated, these 3 there. And as I mentioned, it also has an advantage that you can do you can check the asymmetry there. So because this is a directional index. So So that's yeah. So that's, you can also do it the same thing for the frequency band, because earlier one I showed for the nonlinear index for the broadband raw data, and this is at the frequency band specific. Again, quite a nice resolution. You can find the three pairs are different. So if you put it in a kind of simple, I'm just showing a comparison between 6 or 7. Yes, order of synchrony, you are right. So B is actually the strongest synchronizations, A is then afterwards, and then C is much smaller there. And these separations or these resolutions that somehow for this particular data set are primarily captured by these either phase synchronizations or generalized synchronizations. They're somehow more sensitive about this kind of nature, as well as the getting the nice separations between the cases. I think I mentioned earlier, okay, I just thought in the morning I mentioned, so just I included this one in the afternoon. There I mentioned, because you talk about phase synchrony there, and the phase synchrony, okay, there afterwards it doesn't give you the directional information. I mentioned there is other index, phase slope index, phase lag index. They give you the information about the flow of information. So this is phase slope index. It is rather recent introduced, and it's primarily used or developed to apply on the brain signal. So here this is primarily based on the concept that a non-vanishing part of the imaginary part of the coherence that you cannot explain by the volume conduction effect there. And the volume conduction is usually a notorious problem in the connectivity there. So suppose if you have two signal or two electrodes are very closely spaced, if you get a high synchrony or phase synchrony, that does not necessarily imply that these two electrodes are coupled in phase. That's primarily or very likely to be a spurious artifact, that there is one neural source which contributes to both the signal there, and that is the volume conduction effect there. And definitely you do not want volume conduction to contaminate your functional connectivity analysis, because you expect that the two signals preferably coming from two different systems, two different brain regions. So how you can somehow address this if you have a high density recording? So phase slope index is one way or one approach where you can eliminate the contribution of the connectivity caused by the volume conduction, because volume conduction is instantaneous. So if the volume conduction introduces connectivity, it will be zero order connectivity, means there will not be any delay there. But phase slope index actually is primarily finds a delay there, and what it does, in short, the phase slope index that measures connectivity, or phase lag index, which are kind of very similar, between two signals based on the slope of the phases of their cross spectrum there, because phase slope index primarily measures whether the slope of a phase lag is either consistently positive or consistently negative over several adjacent frequency bands there, and the sign of the phase slope would give you the information whether information flows from A to B or from B to A there. But just remember, although phase slope index is quite a useful index, but it is not a measure of instantaneous connectivity there, and in the brain instantaneous connectivity is more likely the norm. The good neurophysiological reasons that if you record from the surface data or surface level recording, then you are more likely to get zero order connectivity. So that's why even if you use phase slope index, it's always recommended that you also apply traditional phase synchrony analysis as well, which is more sensitive on the zero order or zero lag phase synchrony. Okay, so overall, I mean, there is a one or two I was checking if papers came out, which is giving you a kind of broad overview of all the different available kind of methods, including ours as well. So, overall I mean, you cannot say one method works the best across all scenarios. In short, nonlinear measures like phase synchrony, general synchrony may work better than the linear measures there in most circumstances there, but if your data are non-stationary, then phase synchrony is a better choice. Generalized synchrony, although used a little bit less in the specific task content activity, mainly because it needs a longer period of data, but it is sensitive on weaker interaction. But if your data are really noisy, if you have shorter time samples, then it's still linear methods outperform there, because nonlinear methods are very sensitive to noise there, and the data quality and the data length there. So, in terms of kind of noise performance, in linear methods, okay, it's usually, I mean, additive noise. The linear methods work very well, but more importantly, you should always apply more than one method there to see how much the results change there, because each method has their own assumption, own biases. So, and your data, okay, may not fulfill all the assumptions. So, that is why in order to be sure that what functional connectivity patterns that you get there, to be more confident, you should apply more than one measures. So, that is why I mean, just kind of, this is the slide I like usually. So, linear methods, yes, they are simple there. They have a good analytical backing, very simple to apply, simple to interpret there, but we know that the brain, I mean, brain is non-linear there, but non-linear methods also comes at quite a big cost there, because there is a lot of assumptions, and your data may not meet or very likely to violate a lot of assumptions of nonlinear methods there. On the top of it, you have a lot of methods. There is a misapplications are often quite the norm there, because these days, especially, there are a lot of toolboxes. Earlier times, when possibly 20 years back, when we started, we really have to understand the method before we can apply, because there is no toolbox. We have to program everything, and that means we were more I will not say careful, but at least we had to invest a lot of time before we can apply any method. But these days, thanks to toolboxes, but the downside is you can apply another method without knowing all the intricacies, all the details there. So, that is I was giving an idea that I have seen phase synchrony methods applied on the raw data there, but that means those who ever applied did not actually bother to check that phase does not have a meaning unless it is an oscillation there. So, misapplications often also the norm there. So, but what we want, I mean, despite all this, we want a kind of a much cleaner interpretations, cleaner results, but that only is possible if we are very careful about what methods we use, and also our data quality, data screening, and the assumptions behind the methods, and also to compare across different methods. So, I put this paper as a morning also I mentioned, it one of the first of its kind to somehow give you a reasonably comprehensive, when it was published, overview of the different methods of functional connectivity analysis for EEG and MEG signals. There are quite a few toolboxes. I just highlighted here 3, but there are more there, because nowadays, okay, it's quite a fashion. Anyone publish a new method, they somehow publish their own toolbox. But these toolboxes actually contain, okay, except grandeur causality, which is primarily on the grandeur, which primarily on the causality methods, but both Hermes and eConnectum both offer a different functional connectivity, as well as EEG lab, both field trip, they both offer phase locking index and the phase locking value there. Okay, any question so far? No. So, now that is our official syllabus finished for the exam. So, whatever we will talk about, or for any slides, it won't be, you don't need to worry about exam. But that's, to be honest, this is at the forefront these days of the neuroscience. That's the network analysis there. Earlier we showed how to find whether different electrodes or different sensors which possibly picking up activities from different brain regions, they're interdependent or not. But then the next step is, once we can have a good understanding that whether these different sensors or electrodes are somehow shared, how we can characterize all these patterns of interdependency. So considering brain as a network, and this is somewhat driven by this aspect of the brain as a complex systems there. And complex systems we talked about yesterday, they have a neither completely random nor completely regular. They're in between there. So they show non-trivial characteristics. They consist of several subparts. These subparts are interacting with each other. There is a extensive connections across scales. There is interactions between bottom up and top down, and at the end it is a big systems. Means there is a large number of interacting agents there. And as methods have been developed to deal or to characterize these systems, now slowly we get to understand that although the different complex systems occur in the nature, exist in the nature there, but still all these, despite these various differences at the surface level, still one could express some certain characteristics of these diverse type of complex systems in certain terms of how the underlying network is organized there. And from these developments, now an interdisciplinary field of network science has formed there. And now, as I mentioned, this is the network science is not just forefront of the brain, it is forefront in many branches there. And if you think about network is everywhere. If you consider social network, yes, who you know, we know that important in many fields. There, if you consider the network in, suppose, communication network there, or World Wide Web, or air traffic control, transportation, or even within our body, metabolic network, immunity network there. So everything you can, cellular network, everything you can think of, you will find that there is an complex network underlying it there. And although the kind of interest in understanding the complex network is reasonably recent, last 18 years there, but it started there. I mean, the seed was planted quite a long back in nowadays Russia, earlier times Prussia. That's called the bridges of Königsberg problem there. So that's, to be honest, the origin of network or graph theory. So in early 18th century, it is in 1735, there is a famous Swiss mathematician, his name was Euler. You have heard it about him, I'm sure, Leonhard Euler, Euler's identity, often termed the most beautiful theorem. So Euler was living in this town, Prussian town, Königsberg, which is now the Kaliningrad in current Russia. So this Königsberg, they have 7 bridges there, and there are 2 islands there, and 7 bridges around the river, this river Pregel, and which link these bridges, the main river banks and 2 islands in the middle of the river. You can see the A and the D. Now, those times there was a kind of problem. There was problem. So there was an kind of problems, unsolved problem, that whether it is possible to make a walk crossing exactly one time each of the bridges, 7 bridges, connecting the 2 islands in the river Pregel and its shores. there. So you are not allowed to cross any bridge twice there. And whether it's possible to go everywhere, but you can only allowed to cross the bridge only once there. It was somehow, I don't know who started this, okay, who thought about this, but this problem was somehow, okay, unsolved there. And Euler, who was living that time actually, so he mathematically showed that no, it is not possible there, and he reformulated the same problem by representing the problem as an abstract network. That's called the graph there, and that's the origin of graph theory there. And graph theory, then afterwards, okay, there's a lot of things happen in then later on in 1920s, 1930s or 40s, graph theory was considered, or actually there is an extensive development in the in the mathematics about graph theory. Two famous mathematician, if I recall, one was Paul Erdős. I don't know whether you have heard him. There was a very famous mathematician with a very eccentric lifestyle there, who never had actually any permanent position there, and who published 1,500 papers. Many of them were seminal there. So lived like a very eccentric person. Couldn't drive, okay, there. He just used to say, my brain is open there. So he was like Professor Chakraborty. He used to come to a seminar, he was just sitting there. People would think that he was asleep, and then suddenly he would ask the most insightful question there. So anyway, Paul Erdős, okay, who was a famous, very stalwart in number theory there, but he and another person, yeah, you possibly heard him, Renai. You have heard Renai entropy there. So Renai, okay, also Hungarian, both, because Hungary has a long tradition of mathematics. So Erdős and Renai has a fantastic book called Random Graph Theory. I think it's published in late 40s or early 50s. Yeah. So they were primarily interested in mathematical understanding of random graphs there. So anyway, so what is a graph there? So graph is an abstract representation of a network there. So graph consists of primarily two things. One is the node or the vertices, another is the edges there or the links, whether the two nodes or two vertices are connected or not there. Just simple thing, nothing, just two things. And now the presence of an edge or a link between two vertices would indicate whether these two nodes somehow connected or not there. And if you put it in the EEG, MEG framework, so your node or the vertex could be an electrode or a sensor there, and edges or the links is if you can establish some kind of statistical interdependency between the two signals, right there. So whether you apply functional connectivity or Granger causality or phase synchrony, so all are actually primarily giving you the information whether the two signals are connected or not there. So that's if you are working on the electrode, or we call it signal space, if you are working in the electrode or the sensor space. So here just to show you that, okay, representation of a network as a graph there. So in the case of an unweighted graph there, unweighted graph means you are only interested to find out whether the different vertices are connected or not. That's what your only information, connected. You are not interested that whether, or you don't have much information about how strongly they are connected. And this strength of connection, we call it weight, weights of individual nodes or vertices there. And you can also have a weighted graph there if you have the information how the different nodes there are connected to what strength there. So here I will show you very simple, just a schematic. In this case, as you can see, all the lines are actually have the same somehow thickness. I mean, by the way, this is, ignore that. This is just to show you that to describe the path length. So from A to B, from traversing from A to B, how many links you have to travel there. So here in this case, showing it 3, minimum 3. But otherwise, if you look into the individual the link, they have the same weight there. So that's why it is unweighted there, same thickness. Now if you are looking for weighted graph, so here the same similar thing, but it shows as weighted graph here. So what here indicates or represents, if the line is thicker, means these two nodes there are connected much stronger there. So here the weights of the edges are indicated by how thick the edges are. So graph, okay, is also equivalent as a matrix there. So here the networks, okay, I told earlier the networks are represented as graph, and now I'm telling graph are also equivalent to as a matrices there. Suppose take a simple case here. So there are 5 nodes, that ABCD. This is a square matrix 5 by 5 there. So if there is the diagonal, it's not interesting, because diagonal means how much A is connected with A. So it's not much informative from the network point of view. What you find here, so if there is a gray square, means A is connected with B. Here A is connected with C. So any intersection, if there is a gray square at intersection IJ, means the node I and node J are connected. So suppose here, so this is the data value, data matrix, and if you want to represent this same matrix in the graph, so you can see A is connected with B, A is also connected with C, A is also connected with D, then here B is connected with C, C is connected with D, C is connected also with E, D is only connected with A and C, E is only connected with C. Okay, just the matrix, whether if there is a non-zero values, so these are all other empty squares, means that particular connection doesn't exist there. So this is, you have the matrix. If it is 0, means none, and if there is a positive value here, in this case is 1, there means they are connected there. So you can see, you can also represent a connection, a network diagram by simple in a matrix form there. But importantly, you have to remember that although their informations are somehow represented in equivalent form, but the matrix one does not have the spatial information there. Suppose here it knows that, okay, the way you visualize the node C is very close to A, but the matrix, the way the data are ordered, that doesn't have much of meaning, because you can switch from this row to another row, you can switch it, but the matrix network information would remain the same there. So in a sense, it means your data matrix or the network matrix, we also call connectivity matrix, it contains all the information of the connectivity, but it doesn't have this information about spatial distance, which is, you can think of, okay, often the case. Suppose you have an you have measured from 32 channel EEG, say, and each channel is stored in a column format there. So you have FP1, FP2, and others, the way the system records your channel, but they are stored in an individual column, but that doesn't mean to necessary column always be spatially also very close there. Just to remember that the matrix is a useful visualization of network, but they don't have this information about spatial or topological. Okay, so I already showed an example of connectivity matrix, and because that's the entry point of network analysis. So connectivity matrix, it offers a compact description of the pairwise connectivity between all nodes of a network there. So means by definition, if you have a n number of node, your connectivity matrix would be n n rows, n columns. It's always a square matrix. So for a brain network comprising n nodes, you have a square matrix n by n there. So it has diagonal elements. Diagonal elements, as I mentioned, it doesn't have much information, but although you can put some other relevant information, because you cannot compute a correlation x with x itself. It doesn't make much sense. But in the connectivity, sometimes if you are interested, suppose if you are calculating phase synchrony values between x and y, but in the diagonal you can put the power spectrum values of that particular frequency, how strong the power is, or some other relevant information there. But as such, in the diagonal it doesn't give you much information about the connectivity properties there. But what is relevant? Of diagonal elements there, so which is Cij, and that represents the connectivity between pairs of distinct neural elements or distinct nodes there, and its value and range that depend on what methods you have used there. If you or what methods, what your data, and so forth there. So that's literally your entry point there. And how you, I'll explain to you how you get that. Some other aspects. So far I didn't show you talk about anything about the directionality there. So I showed if node A is connected with B, there is no arrow. But in the network, it's quite sometimes relevant to find out how the information flows from one node to another node there. So the directionality is how you can be expressed in the connectivity matrix. Suppose if you have a different values in the upper and lower triangle, then your connectivity matrix is asymmetric. Think about, suppose you are analyzing all possible pairwise connectivity in the EEG alpha band for a 32 electrodes there. So then you have a 32 by 32 connectivity matrix there. So at each point ij, what you are measuring the phase synchrony in the alpha band between electrode I and electrode j, one value. But phase synchrony is symmetric. So phase synchrony between electrode I and electrode j would be the same as phase synchrony between electrode j and electrode I. So in a connectivity matrix, if you are using phase synchrony, your upper diagonal would be same as the diagonal, the off diagonal element upper and the below there. But suppose if you are using Granger causality, then there we told that it is different because it gives you the directional information. Or if you are using phase slope index or generalized synchrony, then the connectivity between x and y is not the same as connectivity between y and x there. So now then you can put your one directions you can put on the upper diagonal, another direction connectivity you can put in the lower diagonal there. But there are different conventions whether, which way you are going to put, whether you put how much information goes from x to y, whether that you are going to put on the upper, or how much x is influenced by y lower, but it does not matter as long as you stick to the convention because if you want to put how the afferent connection there, so how afferent connection means whether the information is going outside there, then you decide that you are going to put in the row format, then you should always do for all the participants all the conditions in the same way there. So just to give you an idea about there's similarities between the directed weighted directed network or graph from a matrix. Suppose this is your connectivity matrices, and you can see earlier your matrix was symmetric, now it is an asymmetric matrix there. And here in this case, the way the matrix is stored the data, so if any column, if any value here, suppose here it shows that how much A is influencing C, the column is influencing the row. That's the way the matrix is, the values are stored. And you can see here how A is influencing C by 5 and A is being influenced by C by 8 So that's why you can see there is a direction. This is a thinner line, that's a thicker line, because C is influencing more. Similarly, here you can see A is influencing E, that's where A is influencing E, 6. Here C is influencing A, I already showed, and C is influencing F, is much stronger, 20. So that's why it's a much thicker line. Then this one is D is influencing B by 15, also quite strong. And then D is being influenced by E, that's this one. Everything else, there is nothing. So this connectivity matrices, which is kind of showing you, or based on some measures which estimates the asymmetric nature of connectivity, can be represented by this graph. So here, as I mentioned, column was efferent projections, row is afferent projections. Efferent is when information is going out, afferent is information is coming in. You can also have a weighted undirected. Earlier I showed you weighted and directed there at the beginning, just simple binary there. So weighted undirected, everything is here except the arrow, and also because it's undirected, your matrix would be symmetric there along the main diagonal. You can see there's a symmetric matrix. So if there's a connection strength between A and C is 13, the same would be between C and A there. So accordingly, you can reconstruct your graph from the connectivity matrices there. Only here it doesn't give you any information about the direction of information flow or any causal influence that one neural or one node exerts on the another. I showed an example of this binary graph because that's quite important in the network analysis. So earlier, this is the weighted networks, and the binary graph is when there are all the the values in the connectivity matrices is either 1 or 0. There is no weight there. If the nodes are connected, the values are 1. If the nodes are not connected, values would be 0 there. So it's a much simplified version there. Weighted networks is you apply your functional connectivity and then you keep that information how strongly they are connected, but here you only care whether they are somehow connected or not, and that somehow I will come to that point. What is that somehow there? So here you are only interested to tick a box whether they are connected or not. If they are connected, put a 1 in that location in the matrix. If they are not, give it a 0 there. So binary networks tell us where the connections are. It doesn't tell us about the strength of the connection there. So provide no information about variations in connectivity weights between nodes. Now, practically you think that we should care about or give importance about how strongly different brain regions are connected. After all, whatever in methods we're going to use, functional connectivity, they would vary, right? They don't always give the same value there. But there are good reasons that why the binary graph or approach of the measures based on binary graph would be quite useful and informative. The major reason is most of the measures that we apply, or most of the theorems, there are mathematical supports for the graph theory, are primarily applicable for binary graph. There. Weighted graph came much later there. So we get quite a good understanding that even by analyzing or treating the connectivity matrices as just a binary graph there, or just a binary topology of the connectivity matrix, mainly because standard theoretical developments are all based on binary graph there. And you would see the binary graph actually can be quite a meaningful. So this is it is a, I mean, you can also have a binary directed graph as well there. So you just get rid of the weight there, and this is a binary undirected graph, and this is a binary directed graph. Undirected, name suggests it will be symmetric, and connectivity matrix is either 1, or if it's a black means 0 there. Directed graph is an asymmetric matrix here. Here again it shows that, again, if you consider column is influencing, means information flows from node I to node j, and naturally, since it's a binary graph, so there is no differences in weight, so you get all the values, I mean, should be all similar thickness, should be there, although it shows slightly different, but it should be all similar thickness. Okay, so we have another name actually for connectivity matrix, because this is your central input to your graph theory analysis there. It's called adjacency matrix there. Why is adjacency? It's just a name there, but in the graph theory, if the two nodes that are directly connected by an edge are said to be adjacent there, or neighbors. I'm talking again the neighbors, you know, we talked about a lot of times neighbors. So since a matrix which gives you the connection, tells you whether the two nodes are connected or adjacent, or this information about adjacency, that's why it's called adjacency matrix there. So this matrix defines the pattern of pairwise adjacency between the nodes there. So now how you can do binarization there, because all the methods that we discussed, the method gives you a continuous output of the functional connectivity, whether you use a correlation usually you don't use in the EGM, e.g. coherence, phase synchrony, phase slope, or general synchrony, whatever, they are all continuous function. They will give you a continuous output depending on how strongly these two signals are connected. From there, our initial approach is to make the connectivity matrix a kind of consist of either 0 and 1 there. How you can do that? There are various ways, but two most common ways. One is you apply a certain threshold there, certain threshold that if any particular connectivity value is above your threshold, you say, okay, I expect that's a good connection. If it is below the threshold, then you say, no, that's 0 there. It's very, very simple there. So just applying a simple one threshold globally there, you convert a matrix of numbers, all possible different weights, to a matrix of 1 and 0 there. Okay, already 4 o'clock there. Should I? Okay, I can go ahead. Now question is, you can ask, why thresholding there? Why should you threshold? Well, thresholding, as I mentioned, it's important to make a kind of binarization, to do binarizations there, and also threshold helps you to understand the kind of topological patterns between the nodes irrespective of weight variations there, because if you have your just the output of your functional connectivity algorithms there, it will give you always some values. So if depending on if the connectivity is strong, you get higher values. If there is very weak, but still it would not be 0, some values there, very small. Now if you use it just as a weight, as the output of your functional connectivity algorithm, then your connectivity matrix there, it would be filled with all numbers. Means, in a sense, if you want to represent in the graph, it would be every node is connected with every other nodes, only connections weight differ there, but it does not give you the kind of topological patterns there. It only tells you about whether, I mean, assuming each node is connected with all possible nodes, only the connection strength vary depending on the output of your functional connectivity algorithm there. But if we apply binarizations, suddenly you get rid of a lot of connections depending on where you set your threshold. Suddenly the topological properties, okay, would emerge, although you don't know exactly how strongly they are connected there, but still you will see, okay, a kind of whether there is a immediately whether a node has a group of connections with another group of nodes or not. There certain topological aspects, it will be immediately clear, which won't be clear if you use it the raw values there. And also focusing only on the connections and their spatial configurations also provide about the basic architectural plan of the entire network, because often we also want to find out the architectural organization there. And the third point is, importantly, many measures, as I mentioned, based on the network theory or the graph theoretical measures, are much simpler for binary network, not just to compute but to understand, to interpret there. This is because if you have a weighted network, the variations in some topological properties of fully weighted networks is quite difficult to disentangle from the variations in the weight themselves there. But if you have a binary network there, if you find the differences there between the two networks, then you can interpret the result much cleaner as compared to if you find the similar differences between the two weighted networks there, because you cannot tell whether this is because the way the weights are distributed, or this is because the way the network is architecturally organized there. So binary network there, although you are doing a kind of losing a lot of information there, but the results are usually easier to interpret. Okay, should I stop it here for briefly? Yeah. Okay, so it's another 10 minutes break. no screen yet. It's come, hopefully. Okay, so it's a quick recap for you, as well as in the honor of Professor Chakraborty, where so we started from here to introduce the concept of generalized synchronization, where it is assumed that the two systems are connected by some smooth mathematical map. So you first, in order to capture this whether these two systems are interdependent, you do first state space reconstruction, choose a reference vector, find its neighbors, and then choose another reference vector in different state space, find its kind of true neighbors in the state space Y. Then you project with the state space vectors with the same time indices from state space Y to X, and also the vice versa. So in a sense, we call it the mutual neighbors, which has the same time indices of the true neighbors in another state space. The idea is, if the two systems are synchronized geometrically, there will be local smoothness, local topological similarity there. So the set of true neighbors and set of mutual neighbors, they would cluster together and they would lie close to each other. And you can quantify this geometrical proximity and the formation of the neighborhood cloud that consists of true neighbors and mutual neighbors, a simple Euclidean framework, and then you can come up with indices to quantify the functional interdependency between the two systems, those two signals. Then we showed a very simple example of three pairs of signals to apply these different measures on these individual pairs, on the three individual cases: linear correlation, mutual information, coherence in a specific frequency band, then partial derivative coherence, then the phase synchrony, the nonlinear index, frequency specific nonlinear index, and we found that here, at least for these cases, the phase synchrony or the generalized synchrony, they separate these three cases with a better resolution. Then we briefly mentioned about another recently developed index called phase slope index, which is based on the imaginary part of the coherence to get rid of the volume conduction effect. Then it's mentioned that this is good measure, but it's primarily sensitive on a non-instantaneous connectivity there. So that's why this measure should be complemented with other measures which are more sensitive on instantaneous or zero lag phase synchrony. So here we summarize the different methods of functional connectivity measure and highlight the importance of applying more than one method there. Then we talk about the importance of the assumptions, checking, and also to interpret the data accordingly. Some different different MATLAB toolboxes. Then we switch to network analysis, introducing the graph and this historical background, this Königsberg bridge problem, the Euler's famous kind of formation of the graph. Then what does the graph means, the nodes and vertices, and as well as edges, and what are the equivalence representation using EEG, MEG signal, simple graph and matrix, they are equivalent there, and then comes the connectivity matrix. I think you already hear. Okay, so we did a quick recap. Okay, binary graph, and now we're talking about Y thresholding. Yeah, sure. Yeah, I mean, I'm open for questions, any part, any time. Huh? Oh, in the exams? No, in the exams, no. Exams, so you can all sleep. There will be no questions. No. This part, that's why I told from the network analysis, no questions. So you can nicely have a snooze. Okay, so why thresholding? As I mentioned, the thresholding is quite informative binary graph, because many of the classical methods for graph theoretical approaches are kind of based on binary graph there. So how, as I mentioned, so you have to choose a threshold there to decide whether the connectivity the value you get, whether you consider it's higher than the threshold or lower than the threshold. and usually you set it as a global threshold, means the same threshold applies all connectivity there. So how to choose? So usually you should choose in a way, first of all, just general implication, general suggestions that if there are different conditions in your data, so you should choose in a threshold in a way that is independent of the condition of comparisons. So how you can do that? You pool your connectivity values across all conditions there, and then you apply threshold based on the overall kind of distributions, and then you apply on individual adjacency metrics there. Importantly, you should select different threshold for different frequency band, because if you are dealing with EEG or MEG data, then you will find the functional connectivity values, actual value, would be very different depending on which frequency band you are looking at. For example, I told you earlier that low frequency band has a high power there. Similarly, if you apply phase synchrony there, you will find that the low frequency band always give a high absolute values of phase synchrony there. So gamma frequency band give you much smaller value of phase synchrony there. But since you always have to compare within the same frequency band between tasks, but you are not comparing across frequency bands, so absolute values, because that's what usually in your connectivity matrices has. So you should not apply one threshold for all frequency bands there. So for different frequency band, you have to select different threshold.
All bands will have same connectivity or
different connectivity? Naturally, will have a different connectivity. So your connectivity matrices will differ there. Very likely it would be different. So one simple suggestion is you can choose a threshold of 1 standard deviation above the median there. So that's one. So that's about choosing a very simple global threshold. There is another alternative way of thresholding. There, instead of choosing an absolute value, there you apply a threshold while keeping the density of the network same there, because when you apply the earlier kind of fixed threshold, you change the density there, distribution across conditions. But if you here, instead of selecting a fixed value there or fixed threshold, you decide that I will keep only 20% or 30% of the strongest connections there, and then use a rank order which connect pairs, electrode pairs or sensor pairs are the strongest, or the top 30%. So you only keep the top 30% of the edges there. So and then rest, whatever rest, set it to 0 there. There are certain advantages of keeping or doing this kind of density based kind of thresholding as well, because many of the measures are quite sensitive on the density. So this is just to show you, this is taken from the Cohen's book, you can very straight, that's my brain hasn't learned. So this is all the distribution of, suppose this is here, in this case is use the phase lag index. It doesn't matter which index you do, it depends on your choice. So all the distributions, so this is where 1 standard deviation above the median there, and then you apply that this values, this is your kind of a threshold there, and you apply on your connectivity matrices here. Or other one, you can use, so this is another method, ISPC trial distributions, 1 standard deviations, and you created a kind of binary graph. So everything remain 0 except any values which would be equal to 1 above 0.6 there. So that's the way to thresholding from connectivity matrices, which is from all possible values to either 1 and 0, or also you can do a graded thresholding. Here in this case, you keep all the weights above a certain threshold there, and below certain threshold you set it to 0 there. But for simplistic, let's consider, we only consider if the value is above the threshold would be 1, below the threshold would be 0, or we keep it a certain number of connections, provided that number and then 20% or 30% strongest connections. Important point is that whatever threshold you have chosen there, you do need to repeat your subsequent analysis, because afterwards your matrix will be changed, right, from the values to either 1 or 0 or values to some values would remain and others would be set to 0. Then you calculate certain measures. I will talk about that, but it is important that you repeat the whole analysis with a different threshold, just to see, just to inspect that your final outcome is not crucially dependent on the threshold, because whatever I am mentioning, one standard deviation plus mean, but still it is an arbitrary there. So, you have to see whether your arbitrary selection or choice does not change your results qualitatively there. So, it is very important, and also similar thing for the degree as well. So, if you decide you will only keep 30% and then do your analysis afterwards, then you have to do it again, whole analysis, then keeping it, instead of 30%, you keep it 40% or 25% there, and see whether any network based measures qualitatively change or not. So, then your adjacency matrix is now, if it is a simplistic cases, consists of 1 and 0 there, which is original 1 was a functional connectivity, but then which is all numbers, then it transformed to 1 and 0, and then that is your starting point. This is your data here for your network analysis, and then how you want to characterize this network. The one straightforward measure is called the network degree. It means it tells you about the total number of edges. So, how many connections are there in that network? Very simple, just checking how many numbers, how many ones there, and often you calculate, although it is symmetric, but calculate twice there, both upper diagonal and the lower diagonal. And the connectivity degree, then this is about the network degree, about the whole network, and you can also do it at the node level there, finding each node, count how many number of connections it has, how many edges it has there. So, if certain node has many more connections, this is a sign of a hub there. Then you can measure, so second related with the degree is a connection density there. So, connection density is the way you define the measure. It varies between 0, means no connection, to 1, fully connected there. So, it tells you about the overall how strongly the network, how densely the network is connected there. And then another easy, quite immediate measure to characterize the network is the degree distribution there. So, degree distribution, it just tells you about the likelihood that any randomly picked node will have a degree k there. So, it is literally you are primarily kind of plotting the how many nodes have a certain number of links there, and just kind of frequency histogram there. So, histogram you can also present it in the cumulative distribution frame as well. So, it is a plot of pk versus k, and now depending on the network type, you have a different types of degree distributions possible. You can have a Gaussian, binomial, Poisson, exponential, and many others. I haven't listed it, and also power law there. We talked about power law at scale invariant there. So, this degree distribution actually is an important property of a network there. So, if you are considering, put it in the frame, linking with the yesterday's, the power law degree distribution means the network has most of the nodes have very few connections there, but there are few nodes which are massively connected there. So, that is where if you calculate in the log domain, it will be a straight line. Yeah, that is the definition. That is this kind of signature of a network with a scale free degree distribution there. So, most of the nodes, 1 or 2, very few connections, but very few nodes have extensive number of connections. Yeah. So, just to give you one example of scale free distribution, which is one of the first evidence of scale free distribution, not from the EG, but the method of the similar. But I just mentioned showing it to you because this is one of the first evidence, but this is based on fMRI data. Yeah. Usually degree distributions, EEG you do not have that many nodes, so you do not get a good kind of sampling in terms of getting a good distribution. fMRI is good because of a lot of voxels. So, here what you the study was very straightforward. The sub-participants fMRI, which is the bold response, were measured. That also gives you a time series when the participant is doing some task. It is not important here, you will see. And then there is a what they are measuring, what the output is, the each voxels at every moment in time, you get how strongly that voxel is active there, and each voxel has anatomical locations there. So, then you get a time series of the intensities of voxels, and you get thousands of voxels there. So, what you can do, then you calculate the correlations between the voxel intensities there, and then that is the connectivity matrices. This one is the connectivity matrix or correlation matrix, then which is at each point in time, sorry, at each location, that tells you whether these voxels there between I and j, what is the degree of correlation. Simple. And then you apply threshold, simple binary there. So, from here colorful 1, you get a matrix of 1 and 0. So, based on a certain cutoff. So, above a certain correlation, all connections would be set to 1, below that correlation all connections set to 0 there. So, you get a kind of a network there, and then you can calculate the degree distributions here, and that degree distributions, as they found, this is expressed in a very log domain. Here this is the degree k, and that is the count, how many edges have, and that you can see here over almost 10 to the power 1. So, means 10 connections to 100 connections, it is like a decade order. You have a straight line, and that is in the power law, in the evidence of power law. And interesting, you can see here, as I mentioned, here they are plotting on 3 different correlations for 3 different thresholds. So, in one cases they apply a threshold of 0.5. So, all links above 0.5 set to 1, all links below 0.5 set to 0, and then calculate the degree distribution. The same analysis are repeated with our threshold at 0.6, threshold at 0.7, and you can see somehow remains very similar. The slopes remain similar there. So, this degree distribution remains invariant across the choice of the threshold, and it's kind of one of the first evidence of showing large scale brain network is scale free. And interestingly, they did further showing analysis or experiment, so that it does not matter what the participant is doing. When a different task, the power law remains almost invariant across task there. So, anyway, so that show you just a very simple calculation here. You can see just studying the degree distribution there, and that tells you about some nice properties about the network. Another related one, which is often quite used, which is called clustering coefficient. Some of you possibly already have quite a bit of familiarity with network. Those who do not have, clustering coefficient is similar, like I mean, just the word cluster suggests that if you put into the social context, that if I know you and if I know another person, now if we 3 form a cluster, then you and the other person also should know each other there. So, means if you are my friend there, so your friend's friend is also my friend there. So, that means there is a triad, at least a minimum, because in order to find a cluster you need to have at least 3 nodes there. So, to form a cluster there, and this clustering coefficient you can both measure at the local node level as well as at the global kind of network level there. So, clustering coefficients often is a signature of or a good index of the local structure there, and interpreted as kind of resilience to we call it a random omission of if certain links is impaired, it does not have much impact on the network operations there. And importantly, the clustering coefficient is primarily based on suprathreshold connections, not based on whether the 2 nodes are physically close or not. You only matter whether they 2 share or have share informations or not. Another related concept of the characteristics of the network we call characteristic path length there. So, characteristic path length means if you want to travel from in the network from one node to another node, how many node you have to traverse in between there. So, if the network, okay, if it is considered if the network is very hierarchical, then you have to go in between a lot of steps there. But if somehow if there is some shortcut there, so then the characteristic path length would be quite small there, because then any two nodes randomly selected in the network, they have somehow there is certain shortcut there. But if the network is very hierarchical, very feed forward, then going from a very top level to the bottom level, you have to go along all the hierarchy. Then the characteristic path length would be quite high there. So, what is the mean clustering? Characteristic path length is the shortest path length between all pairs of nodes in a network there. And this characteristic path length is a very reliable measure of integration in the brain networks there, because if the network has a short characteristic path length, they are supposed to integrate information much more efficiently, because just as I mentioned, there is some shortcut there, so that information can transmit more efficiently, faster. Otherwise, if a network is fully ordered or fully clustered, then information from one point to another point might you have a lot of intermediate steps.
This should then depend upon the task you have to perform at the moment.
And this is
Deorganized.
yes, but you can also apply principally all these measures also on the static anatomic network as well. But you are right, functional network, and definitely depends on the task, what task you perform, all the network characteristics might change. But the concept wise, these you also can apply on a structured data. But we are not talking here about the structural data here. Structural data means, if we remember earlier talking about, you can measure this called the DTI data, the diffusion tensor imaging there. So, there it tells about whether the different structures in the different regions of the brain, they are connected or not there, by primarily measuring the water anisotropic there, and there you can apply these measures on the DTI or in the but in the EEG MEG sense, yes, it is a functional. You can apply all this network analysis. There has been loads of applications, hundreds and hundreds. I didn't mention anything application, mainly because there are too many, both on spontaneous state and also during the task there. And naturally it changes. Suppose one example comes to my mind, that characteristic path length, because shorter characteristic path length means information transferred from one part of the network to another part of network much faster. And it has been found that the characteristic path length is inversely correlated with intelligence there. With intelligence, so means higher intelligence, shorter characteristic path length there, which makes sense. So, shorter path length means information on average be routed between pairs of nodes using only a few edges. There is always some kind of shortcut always there. And what are the implications? Because if information does not need to pass along many edges, so means it will reduce the metabolic cost there. It will also require less energy, and the process would be much faster, more direct, and less noisy there. This kind of three core measures, this degree distribution, clustering coefficient, and characteristic path length, can principally distinguish the four major types of network, which is a very ordered and clustered network, random network, the small world network, and the scale-free network there. And I will mention to you there, because again, like functional connectivity, because once you have a matrix, a network, you can characterize this network in very many ways there. So, I think it is beyond the kind of the scope or also counterproductive to list all possible different measures the way you characterize. I give you some references, okay, which talks about very many different measures that you can calculate, but I just here highlight the main principal measures by which you usually characterize the brain network. And the three are this degree distribution, clustering coefficient, and characteristic path length. So, three basic networks. That's the very ordered, fully ordered network, then the small world and the random. So, ordered network is, you can see there each node is connected to its nearest neighbors. There, it's a very ordered, very class. Oh, again, I'm going there. So here, so each node is only connected, okay, either 2 neighbors or 4 neighbors here. So it's a local clustering. There, everything is perfectly ordered there. This very ordered network, by construction, it has a very high clustering there, but its characteristic path length is also very high there. Suppose for whatever reasons, I mean, if information has to go from here to there, so it has to go from there, then jump from here, then jump from here there. So it's quite a few nodes it has to traverse there. Locally, it is very clustered, so that's why you get a high clustering coefficient there, but its path length would be quite large there. Small world network, which is very similar, you can see here network wise, it has a very strong local clustering. So its neighbors are somehow, you are connected with your neighbors, but in between there are some random connections, a few, not many there. And this network, which is primarily heavily clustered, locally clustered, but with some random, just a few random rewiring, actually reduces the network characteristic path length drastically, or makes the network very efficient, while still maintaining the high clustering. So this network, kind of network, which have a very high clustering, but also have a low characteristic path length, means information can transmit very efficiently. Suppose earlier I was telling you, if I have to travel from here to there, so I go from here and then suddenly I found a shortcut here, and this shortcut does not need to be very, okay, in order for the network to display or exhibit this low characteristic path length, it can be random, these random connections there. So small world network in a sense can be thought of as an ordered network where only a small fraction of vertices are just randomly rewired there, and then in those kind of network the clustering would be as high as proper regular clustered network, but its efficiency and the information processing efficiency, or as characterized by the characteristic path length, would be as good as a random network. So random networks, which is on the right, so everything is connected with each other randomly there. So it has information actually, the characteristic path length is very low there. If you pick up any two randomly, suppose I am talking about here, okay, this, if you here to here, you can see suddenly there is a shortcut from here. There are random connections there, but still that reduces the characteristic path length there.
You can't go to the neighbor.
That's right. You can also go to neighbor, but on average, you get a much smaller characteristic path length if you calculate overall nodes. But what you do not have is clustering there. And okay, yeah, and then the last one, as I mentioned, this another one I already showed some evidence, that's called the scale-free network. So scale-free network, as it suggests, it has a network with a power law degree distribution there. And scale-free network, in terms of clustering, it is less clustered than small world there, but characteristic path length is also quite small there. And now if you look into the actual brain network, the brain network is somehow in between. They show some properties of small world network, as well as I showed also properties of the scale free network there. So it's a kind of how the way the brain network is organized is a kind of intermediate structure between these extremes, from very locally connected, highly ordered regular network and a random network and a scale-free network there. So it's somehow intermediate or in between. And this kind of combination, this placing it at the intermediate, which is some mixture of some of the properties from each of these standard networks, that very likely provides a balance between the segregation and integration. Because we know in the brain, the certain brain regions are quite relevant for processing only certain type of information. So there is a certain aspect of segregation there. At the same time, we also know that the different brain regions are also highly densely interconnected there. So you need some aspect of segregation and some also aspect of integration there. What is the advantage of small world? Because small world also shows a high clustering, and in the brain you also find the nearby neurons, okay, or the neurons at one particular patch, they often are somehow connected with other nearby neurons, so form a local high clustering. But also you have some in the small world, it happens to have a random clustering which reduces the characteristic path length, and this having this reduced characteristic path lengths, so that lead to, as I mentioned, information processing would be more faster, more optimized at a reduced wearing cost there, because wearing cost for a random network is much high there. But if you have only a few randomized links there, but still you get a very highly efficient information processing point of view. So means you are reducing the wearing cost as well as same time achieving optimal information processing there. And then comes the scale-free network. So scale-free network, as I mentioned earlier, because it has a scale-free degree distribution. Most of the nodes, only few connections. But there are some nodes which are hub, means it is connected to many other regions, many other nodes there. And we know there is also in the brain, I showed already the statistical evidence of scale-free regions, and there is another concept called rich club there. Rich club structure means those which are hub, means those which have a lot of connections, they are also connected with each other there. So that's we call or the network terminologies called the rich club structure. And latest evidence suggests that there are dozens of brain areas which satisfy this rich club architecture there. For example, there's one brain region called insula there, precuneus there, which shows the maximum connections there with all other brain regions, as well as other brain regions like hippocampus. I mentioned hippocampus because that's very important for processing memory there. Precuneus, very important. I mean, we only can speculate what it does, but it is quite crucial in processing self-related informations. Or frontal cortex there. There are, I think, around a dozen has been identified which satisfy this rich club architecture. Now think about, so this is about the optimization of information processing there. Now think from other evolutionary aspects. So suppose how robust this individual network, because evolution wise you want your system to be very robust, your network to be robust against external attack, right? Now if you consider the scale-free network, because scale-free network, what happens, you have majority of the nodes are very few connection there. So if you destroy some of the nodes, it don't have much impact on the operation there. But there is a problem if you attack the hub there. Think about the World Wide Web there. If you take out drastically 5% randomly of the suppose randomly 5% of the websites, it possibly will not matter provided Google or other server is unaffected. If you target Google or Facebook, then then suddenly there would be the whole network would literally collapse there. So similarly in the brain, there are certain regions of the brain there, if they somehow gets impaired there, then you will have an effect overall whole network there. And that's exactly has been found by applying this kind of technique to the brain in impairment there. So they found whenever there is a brain is or the patient is severely impaired in different neurological disease like Alzheimer's or multiple sclerosis, one or another hubs are somehow very much affected there. On the other hand, evolutionary also, if you consider the brain is a very robust, because if you just randomly destroy some of the links, it has very strong resilient properties, because most of the connections or most of the nodes are very few connections if it's a scale-free nature there. So that's why if there is some arbitrary perturbations at arbitrary locations on the brain, it has minimal impact there. On the other hand, brain also shows a kind of small world features, because small world is a very good candidate to have this optimized information processing there. So scale-free network shows you about the presence of hub. In the small world, you see there is nothing hub there. The hub, that certain nodes are very prominent, as if hubs are like banks. If the one bank collapse, the whole economy would collapse there. So you don't find those kind of important of hub or a presence of hub in the small world network. You will find mainly in the scale-free network. So the brain, in the actual data, you find the brain, they show both the small world as well as the scale-free nature. So the network features of a healthy brain across, I would say, possibly a few hundred studies have done, only on the possibly more than a few hundred. Okay, each year these days published possibly 1,000 on the application of network on the brain. So it shows high clustering, short characteristic path length. It also shows hierarchical modularity and scale-free degree distribution, and most importantly, presence of hubs there. And these hubs are also somehow connected with each other, forming a rich club. And that has been anatomically found, not functionally. By using anatomical anatomical data, tracing data, they identified those regions in the brain which kind of form this rich club. They are densely connected, and also they are densely connected with each other.
If you go words on what you just said, exemplify what you just said.
Just says is there are certain parts in the brain which are heavily connected with all other parts of the brain, and also those who have a high connection to other parts of the brain, they are also connected with themselves there. This is this connectivity. Oh, this is done based on the DTI data, diffusion tensor imaging there. So that's not the functional. There's a DTI data there, but you have an implications also has been found in the functional data by analyzing EEG based connectivity, analyzing MEG based connectivity, or analyzing fMRI based connectivity, where researchers found that with the disease, there is first of all there is a strong impact. You find the characteristic path length and also impact on the clustering, and also we call it the impact, we call it overloading hub there. So the hub, there is a failure in this processing of certain hub, although depending on the disease, your type of what kind of network damage you expect, that change there. But invariably there, all the disease that, I mean what researchers have studied from schizophrenia, depression, Alzheimer's, there is lots of literature on Alzheimer's, different types of MCI, which is mild cognitive impairment, multiple sclerosis, epilepsy. There is a strong alteration in the brain network from healthy functioning. And this one actually is a heavily cited paper which gives you a very nice overview of actually a toolbox, MATLAB based toolbox, which allows you to compute the different connectivity measures as well as a list of various measures that you can calculate. Here I talk about mainly a few, which are the principal, degree distribution, clustering coefficient, characteristic path length, but those are by no means the only one. Okay. So this one paper is heavily cited paper. So, now although I introduced this aspect of network theory in a kind of more general way, now if you want to use it for the EEG, MEG data, there are a couple of things you have to keep in mind. The first is where you want to apply your network. Do you want to apply a network on the electrode or sensor space or on the source space? There, electrode or sensor space means you have suppose 32 electrode or 64 electrode, and then assuming each electrode has a node, and then you calculate your functional connectivity indices between all pairs of 32 pairs there. But we know that, as I mentioned earlier, that because of the mixing problems, the one electrode or one channel not only contains information about underlying sources, but also information from its nearby sources there. So, there is a mixing problem and the volume conduction effects there. So, it might be not a bad idea to apply your network analysis on the source space, means you apply source reconstruction algorithm, try to solve your inverse problem, preferably distributed source imaging. So, then you are approximating your sensor space data, sensor level data by distributed sources, depending on what source algorithm you use, and then you apply your connectivity algorithm on the source level there. But you have to remember that, I mean, then you have a much stronger, I would say, better position to interpret the data, but we all know source reconstruction is not straightforward. It's based on a lot of assumptions there. Usually this approach works well if you have an MEG data, or also if you have a high density EEG data there. And that leads to the second point, that EEG data reference is a big issue. I showed you already that reference sometimes change your results. How it changes the network, to be honest, very little has been done there. So, that's you have to be careful there. If you want to compare with a previous literature, so preferably follow the same montage there. Selection of epochs there, or I would say rather duration of epochs there. Depending on what functional connectivity methods you use, that should determine or influence your choice of duration of epochs, because some methods need a longer duration there. And this is a non-trivial decision. Choice of frequency bands. Yes, we are interested in understanding brain network in different frequencies, but then if you can think of that, if we are interested in finding the statistically significant differences between the networks, then we are not, by applying the network theory, you are also increasing the dimensions, because for every different frequencies there, if you want to also measure the node based information, so node based degree, node based characteristic path, the path length, then naturally you have a lot of more comparisons there, statistical comparisons, and then we know the notorious problem of multiple comparison comes into play there. So, it's preferably, I would say, recommended that you know which frequency to target. Instead of looking at all possible frequency bands, you already pre-select. So, this is the frequency band of my choice. That is where I expect things should happen based on the previous literature. So, that you have a more hypothesis driven approach. And the last one, which is less studied, that so far I talked about the network considering as a static. On the other hand, I told at the beginning, functional network are transient, they change their characteristics with time. So, it would be quite important and interesting and crucial actually to characterize the temporal variations of the network. So far majority of the research literature primarily treat the network as a static over a period of time. So, it would be quite, I mean, only recently there are some research literature which started looking at the temporal variation of the network there. So, this is a kind of interesting paper published last year, which talks about these different practical aspects if you are interested in studying network applied to EEG and MEG data, because as I mentioned, network as such is a theory which was developed outside the brain. It was developed as a mathematics kind of random matrix theory. It's come from, I'm sorry, random graph theory, not matrix, random graph theory. Then later on in 1998, there is a paper published in Nature where they showed the application of this random graph theory on simple data set like the neural network of C. elegans, which is a worm there, or network of this I mentioned actors, and then they found the presence of small world, and that has 1998, so it's pretty recent, that has kick-started the whole field there, and then afterwards it's exploded there. So majority of the papers you will find they're not from EEG and MEG, they will find from fMRI or anatomical tracings, or DTI now it is very popular, but at the same time EEG, MEG also will have a, if I'm sure a few, more than 1,000 papers there. So it's a very rapidly expanding field there. So, but at the same time, as you know, this is like earlier, you can apply a lot of measures to your data, but it's important to careful applications there. You can find something, but whether that really means something or not, for that you really need to be careful. Okay, so network analysis, I didn't give you any applications here because there are really too many applications. I gave you some papers, they are the least some of the applications, but literally you can take any task, any disease there, you will find alterations in the network or topology. That's to be honest. So anyway, network analysis provides a new insight into the topological and dynamical properties of brain networks, and also it's allows to understand the correlations between a specific network architecture, network structure, and also the processes that takes place in the network. And the third is, which is these days more common, that the different network measures are found to be quite useful as a biomarkers there, or early detection of a certain disease. Certain issues, interpretation problems, like any mathematical methods, when it applied on real data, because all other things, all these concepts were developed outside neuroscience there, but we are applying them on the neural data, so interpretation always is a problem there, because the methods are not developed to study the brain in mind there. And also there is a lot of variations you will find there. Some papers would say, oh, network, this high clustering increases in certain disease. Someone says, no, clustering decreases for the similar type of disease. Both are right. It's mainly this variation is caused by, first of all, one possibly uses one particular type of imaging there, or someone uses invasive data there, or also someone uses one type of functional connectivity methods, or even another type of the processing steps in the calculating the network measures. Depending on what threshold you use, what kind of thresholding, that also has an impact there. And that leads to the next point, whether you also have a proper control network to compare with. If you remember, I emphasized many times, this is the way the importance of surrogate data. So you always need to have a good control data to compare your results there, because these are application of mathematical methods on the real data there. So it's important, in order to be convinced, before you are convinced about whether this measure gives you something insightful, you really have to have a good statistical control. Surrogate data I talk about, same surrogate data application can also be applied to the network analysis as well there. So you can repeat, there are different ways of surrogate analysis possible. One way is, suppose you have this, repeat the whole analysis, entire analysis from the functional connectivity by replacing each raw data by its surrogates there. That's a one more intensive way of controlling. Another one is, you have your connectivity matrix on the raw or actual data. Then what you can do, you create a random matrix which shares some of the properties, same number of nodes, or you just shuffle the locations or shuffle the edges there, and then you calculate your degree distributions, and degree distribution is the same. You calculate your clustering coefficient and characteristic path length of your actual data and also the shuffle data there. So you do need a good way of comparing your actual values with a set of statistically controlled kind of network. Thresholding problems, yes, it remains a problem there. Nowadays, I showed here primarily binary network because it is easier to interpret, but now more and more weighted networks are used there, and there also the problem is at some point you also have to apply the threshold. Where to apply the threshold? There. Multiple comparison problems, if you have many more measures there, many more frequencies, many more measures, you will have suffer from multiple comparison problem, because then you cannot differentiate whether the differences that you get, whether they are statistically robust or not. And the last is mindless application there, because again there are toolboxes there, you have the data, so it's very tempting to just apply and to just if you get some significant answer, you got it. But no, it should not work that way. You really have to understand why first of all you choose this particular method, why do you think there have been expected differences. Even I have seen papers published, suppose 10 channel data applying network, but actually that's meaningless. I mean, you cannot get a reasonable network measures based on a network of 10 nodes there. So anyway, so this is the question is, you know, this is currently that there is a good availability of different advanced methods there, but it's important that we take an informed decisions. We understand what each method does, what are its constraints, and accordingly we choose the method. That's what I call the mindless applications there. Yes, the software, there is a brain connectivity toolbox, that's the most widely used the network analysis toolbox, which is linked with the paper earlier I showed you. That's done, it's kind of maintained by Olaf Sporns. He has a very nice book there, Complex Brain Network there for non-technical. And there is another recent book I didn't mention, came out just last month, which is a very good book if you really want to invest in the network. They talk about all possible network, not just EEG, MEG, mainly about fMRI and the network mathematics, understanding of mathematics of the network by Fornito, Bullmore, and I think Zaleski. Bullmore is the last author. Came out last month. And this website I found actually a couple of days back, which lists all the good softwares, not just about the network analysis, good software, good data sets about the neuroscience. It's quite resourceful. Okay, so I'll stop here. Yes.
Could you go to the slide where you have shown 3 different networks ordered and before this one?
Yeah.
Could you explain that probability of
Oh, the rewiring probability. So rewiring probability is a primarily tell you that when probability is 1, then you literally your network becomes fully random there. So how many, so here if you have at the very left hand side, so you only rewire a few nodes. If you are on the 1, means you are rewiring all possible nodes, so means your network is literally become random. So it's like rewiring, so you are just randomly picking up nodes and connecting them randomly. So rewiring probability, if it's a 0, means you are not changing any rewire, you are not doing any rewiring. If you do 1, it's a probability, means you are rewiring all nodes, all edges there. 1, your rewiring probability is 1, then whole network becomes random.
And when we are learning a task or learning something new, there is rewiring happening in the brain.
That is right, you expect,
So,
yes.
The center one is the one that is more represents the brain network, right?
So actually you have not really, I mean surely you have a lot of small world properties, okay, there. I mean the small world property, you are right, small world properties also have a high clustering, that's right there. But this is small world properties you find not just in the learning, but in a standard default configurations there, and also properties of scale free network as well there. Only thing is you have to remember the learning one there, this rewiring there, yes, surely rewiring happens. Now the question is, can we expect to detect those subtle rewiring by EEG? That's the first. Second problem is, I mean this is difficult issues, because usually you expect the learning related rewiring primarily happening at a much synaptic level, much micro level where EEG is not picking up. And the second is you expect that these learning related changes happen are usually a much slower process there, compared to an EEG that you are measuring right now there. So, from the functional level or from the surface level data, you might find, I haven't checked it, you might find some evidence of learning related some different effects, but I think you may not get that clear demonstration or evidence from the surface level recording of the learning related neuroplasticity there, because that's happening at a much micro level there. And also another one interesting would be, okay, there and interesting would be if you do it just as speculations there, because often the learning related changes happen during sleep there, not actually during the learning. It happens during the sleep, because when we are learning a new task, there has been a considerable body of evidence suggests that when we are learning a new task there, and then during the sleep our brain replays the things that we have learned or things that we are being exposed to, brain replays those, literally replays like a camera there, and that we call it consolidation, and that consolidation process is very crucial there. So, it would be interesting to see, I don't know, if you have a high, okay, no, I mean EEG is difficult to capture. I mean, although a lot of EEG studies done not to detect those changes, EEG studies has done to show that if you disrupt certain stages in sleep while you are learning a skill, then your learning performance would also be disrupted there. So, an interesting food for thought to see whether, okay, certain brain rewiring takes place during sleep. But we know that consolidation does take place in the sleep, and there is a replay of the activation, or we call it reactivation of the brain patterns happen in the sleep. Reactivation of task related brain patterns happen in the sleep, even that has been found at the single cell level. And actually most of the studies are done in the single cell level there. So, the sleep is very good. If you are learning something, it's important that you sleep. That's usually the nature's best medicine for learning there. So, if you disrupt sleep, you literally, okay, reducing the chance of learning there.
How more change with age, young people?
In what sense? Yeah, there is a big change in the network. Big change in the network. There is lots of studies that age related changes in the brain, even in a healthy, not with the MCI, not in Alzheimer's, but there is a big literature. There is also, okay, big changes at the very early stage, and especially at the early stage when suddenly at certain stage, I forgot exactly what age, there is a small world type network properties emerges, which shows as the brain suddenly becomes more information processing wise efficient. But at certain stages of the early developmental phase, you also find changes in the network, and definitely there is a considerable changes in the network topology in the later stage. In healthy aging brain, or a healthy brain we undergoing aging, as well as in the certain disease associated, okay, with memory impairment, Alzheimer's.
Teenage is when last changes take place.
Teenagers, okay, yes, there is I mean, used to be kind of, we knew very little, but for the last 5 or 10 years there has been quite a bit of research done on what happens in the adolescent brains. Yeah, there is a major changes happen in the emotional circuitry, as far as I know. I'm not an expert on the teenage, I mean research on the teenage, but usually the major changes happen in the emotional circuit. There, a lot of, okay, pruning and rewiring there, and that's why whatever we do at the teenage time, the theory is that leaves a strong imprint. Whatever music you listen to, you will find, okay, that would stick to your brain. So that you'll always tend to like the music, or okay, or something which is emotionally connected at the teenage years there. So they are kind of sticky, kind of glue to the brain there. Anything else? Everything clear? All the network is working fine, small world, the earth scale free. So, which, if I give you a choice, which network you like to have, small world or scale free?
Sometimes small, sometimes big.
That's a good idea. Best of both worlds. I mean, the scale free somehow tell you about which is how the world. I mean, and the society works. Means some scale free means if you could take economic distribution, money distribution, that's a scale free, because most of us don't have much money, but there are a few people who have enormous amount of money there. And that's the same thing also in the brain. There are majority of the nodes or kind of patches or neural regions that don't have much connections, but some have enormous connections there. But the advantage is these are very robust against random attack there. But targeted attack there, if you want to really try to hack the Google or try to hack the Facebook, then everything would collapse. But targeted usually in the nature, in the evolution point of view, very unlikely to face targeted attack there, because if you want to face targeted attack means another very intelligent species or something is somehow doing. So it's, you have to be, evolutionary point of view, it makes more sense to have stronger or kind of robust against random attack there. On the other hand, if you have a small world network, it's very informationally efficient there, but it's highly clustered there. So means if you randomly take out some, you literally lose quite a bit of informations, whatever that node is particularly doing there. So which is often found, suppose in the brain, suppose if you have someone has a stroke, if it affects the language network there, because it's highly clustered, only very focal stroke effect, but he or she unfortunately loses the ability to speech there. Although it's a random attack, you can see here it's nothing targeted there. So that's the problem of small world network, the high cost of it is less robust against external perturbation there or external kind of attack, because the way the network is highly clustered there. So the moment you take out some a clustering, it has quite a strong impact on the kind of performance there. On the other hand, healthy wise, its small world network is optimized in terms of wearing cost, energy. So you have to have a hard choice which one to choose. So that's why the nature chooses both there. So you have an evidence of both small world and scale free there, and there has been a good body of evidence that how you can somehow computationally what kind of neural geometry, the way the neuron branches out, because that's what the network is formed. The network is in how this network works. Suppose in the human, we don't know yet, because that's very difficult to do, to trace so many, but if it has been done on worm there. Suppose take an example of C. elegans, where you know exactly the kind of almost every neuron we know. It has 300 some neurons. So it has been found that for the C. elegans there, so usually the neurons tend to start or connect only at the locally there, and as the worm reaches adulthood or worm goes into somehow grows becoming adult, then the shorter distance, shorter connection becomes longer there. So that means if any connection which is longer, that is older connection there. We don't know about exactly what happened in the brain there, I mean human brain there, but it suggests that this kind of aspect of the clustering, yes, that's how initial started, but then later on very likely as we gather more experiences, because as I mentioned, all this anatomical connectivity is also shaped by functional connectivity, but shaped by our experiences. We talked about neural plasticity, so all these things are interconnected there. Okay, so I have talked enough. If there is no
some people learn languages pretty easily.
Yes.
Several languages. But some people find it hard to learn more than 2 or 3 languages.
Yes, and also you can I can give you another one example. I mean, although we said learn languages, I mean we know that usually we know reasonably well that if you start learning a language before age of 12 or 11, you are in a better position to learn a language. But that doesn't mean that as an adult you cannot. You can. There. Some people who are polyglot, yeah, there are some brain imaging studies. They found, I can't remember exactly where. I know they have a better kind of parietal lobe enlarged, but I can't remember all the details of exactly where in the brain, what are the brain regions that differ. But the problem of these kind of studies are, we cannot tell or distinguish correlation from the causation. So we cannot tell whether the brain is changed or this different structure of the brain that is causing them to learn a language, or the brain is changed by learning these two languages. So that's whether one of the problems of correlation from causation. But another one, there's another interesting aspect you will find, that some people can not only pick up but also can imitate the accent there, or pick up the accent. And usually children, if they start at the early age, they can pick up the accent of another language. Adult, we very struggle there. That's where usually, even if we learn the rules, okay, there, what we struggle is the accent. And the recent research suggests that it's very interesting. There are certain brain circuits which are relevant for empathy there. So if you have a higher empathy, then you are better or more likely to pick up the accent of a foreign language there, because accent is also kind of a proxy of group membership there, whether you belong to a certain group or not there. And empathy is again, you can share other persons, or not just share, also to feel other persons the pain or other emotions there. So there's some very recent research suggests that even in the anatomically there is that empathic, those brain circuits which are relevant for processing empathy, they're better, or they are more connected for those adult individuals who are better in picking up accents of another language. Okay. And we have shown even earlier that when you process your own language versus when you process another different languages, your brain network change. Yeah. We showed a few years back. So that other people have also shown. And not only that, we showed that your if you are proficient in as a bilingual, then how you process your own language is also been changed compared to someone who is only monolingual. So that's, we call it the feedback effect. So learning another language would changes or influences the way you process your own language there, and that can be influenced or can be seen by the brain network there. Okay. You guys are working on meditation. There's lots of studies on brain network in meditation. There are changes in the after 8 weeks meditation, both in the structural as well as functional. There. Okay. Okay, fine. So tomorrow I will. Okay, I mean you have seen, I think, almost 600 slides. So tomorrow I will try not to make much slides. We will talk tomorrow. There. Enough of slides. What topic of tomorrow? Okay, it's up to these guys, because tomorrow I like to hear from them. I have talked so much all the time. So tomorrow is a more like, okay, I'll mention a little bit at the beginning how we can modulate the brain oscillations. We talk about so far how we can record, how we understand, and now what are the ways we can modulate the brain oscillations. A little bit, that's in the morning. Then afterwards open for the house, and I like to hear from them. So I have talked continuously and showing how to become a cognitive neuroscientist. Okay, and those something I like to hear from them. In the afternoon. In the morning, I'll talk a little bit on how we can modulate brain oscillations. There. Day after they have to exam.